Yeah, it's your boy Chili here. Welcome back to ROM Hacking. I'm going to be starting my playthrough, but like I said before, it's not all fun and games. We're going to be watching for a bunch of things, and one of the main things that we're watching for is what parts of the RAM are actually being used, because we need to find places that we can use ourselves to persist some data as we run the game. Here's the batch that I used to start the emulator. This part is the same we've been using before, but we add this log option that'll enable the error log file, and that is going to be very useful for us. So let's run this emulator, and we are going to execute it. We're not going to do anything until we get to the start menu. That's a very important detail. Now we're at the start menu. We're going to pause emulation, and we want to run this command to set up a watch point. So this is going to watch the entire RAM, read and write, and every time we hit the watch point, we're going to log the address that was accessed to the error log file, and then we're going to resume emulation. So we can play the game and it'll spit out every single address every time it does an access to the RAM. So first we do this, and that makes the watch point show up here. And then we resume the game, and right away you're gonna notice, let me just click on my window so I can use it don't look so hot. It's feeling a little sick. Still sick with it. But let's check what happens. Error.log. Okay, so we got a 29 megabyte file for running that for like a few seconds. Gonna look in here. You can see this is interesting stuff. We'll be looking at this again later, but here's what all of our outputs that came from our watch point. We can see it's accessing like the same location in memory very often, but if we scroll down, we'll find other places where it's actually doing work, and it is accessing a whole bunch of different places in RAM. All right, so we have this. We can use these memory locations, these addresses, to build a map of what addresses have been accessed, and more importantly, what addresses remain that we might be able to use. And I could just basically run this and play through the entire game, and that would give me pretty good confidence about, okay, these regions of RAM are probably safe for me to use. Now the problem is, of course, it ain't exactly the fastest gun in the West. But bear with me here. So we run our thing. It runs very slow. We get a trace of a lot of addresses that have been accessed. So let's just say that, these blue things are, okay, regions of memory, that were being accessed. So we have a pool of candidate addresses. And initially, that's just all the addresses from 0 to, 64K. We subtract the ones that have been accessed. So we now have a pool of significantly fewer addresses. And from that pool, we can extract regions. We can say, okay, so this region, these ones in this region haven't been accessed. So now, instead of doing a watch over the entire region of memory, we do a few watches over these regions. We have reduced the scope of RAM that we are watching. And because we've reduced the scope of RAM, now it's not hitting the watch points as often, and so the game will run fine. And then we can now play through the game a little further. We will get a new list of regions. Okay, so as we play further in the game, it accesses more regions that it never accessed before. So now it accesses, here and here and here and here and here and here. And so now we can reduce the scope of our watch points even further. And as we reduce it, the game plays better. Our log file doesn't blow up, and we can basically play through the entire game and it'll work fine. And every time we end a play session, if there are new regions of RAM that have been accessed, we update. So obviously this would be very annoying to do by hand. And so that's why I wrote this Python script to do it for me. I say I wrote it, but I wrote 20%. ChatGPT probably wrote 80% of it. But yeah, you get the idea. So we put in our error log. It's got a bunch of addresses. What the Python script does is, it's got 3 commands in here: update map, process ranges, generate script. So update map, what it's going to do is it's going to read in error.log. It's going to figure out, okay, what are the set of addresses that have been accessed. It does that. Here, it parses in the lines. It uses a set to remove duplicates, and then it turns that into a list. And then what you're going to do is you're going to have this candidates file. And initially, candidates is just the entire set of all addresses in the RAM space. And then you subtract the ones that were visited, and you get a new candidates file. And every time I run this, it generates candidates 2, candidates 3. And these files get progressively shorter. So candidates... Now, there are a couple gotchas that you gotta realize here, or you're gonna have a bad time. Number one is, okay, so imagine I run my trace. I see... here, I just blow up the address space a little bit. I've got 9 bytes of memory here. And I see, okay, so I got an access at byte 0, and I got an access at byte 4. And so I could interpret that as saying, okay, so that means that 1, 2, 3, 5, 6, 7 are available. But that's not necessarily the case. When the watch point detects an access at address 0, that could have been an access 1 byte, but that could have also been a 32-bit access. So there's some ambiguity. It could mean that there's a bunch of bytes available, or it could mean that those two accesses were actually cover all 8 bytes in this region. And so for that reason, what I'm doing is when I extract regions to watch, the region, the range of bytes, free bytes, has to be greater than 8 bytes. So if I have a section that's greater than 8 bytes, if I have an access here and an access here, I know that because this one can only be maximum 4, that these ones have to at least be still free. You know what I'm saying? So I only consider regions bigger than 4 bytes long, and that protects me against this ambiguity. Now, the other thing that you have to be careful about when doing this is when you start your watch. Because if you start it when the Genesis boots, it's going to run a routine that basically runs through a bunch of the RAM and just fills it with a specific value. But we don't care about that, so we don't want to log that, because that'll just basically eliminate almost all the RAM from our usable RAM. We only care about the RAM that's being used when you're actually playing the game. So we don't want to start at the very beginning when you boot the Genesis. We want to start basically from the menu when you actually start playing the game. All right, so let's say I did the watching. I watched the whole range of RAM, had a huge log file. I imported that, and I got my first list of candidates here. These are addresses for which a access has not been logged. So the next step to do that is, well, I got to make sure I haven't automated everything here. So I got to change this input to be candidates 1. And we're going to find the ranges of memory that are available. They have to be greater. Yeah, this check here supposedly checks for ranges that are only greater than 8 bytes. Process ranges. So step 1 was step 1 was 3, which is update map. It's a little confusing. I hacked this all together. Step 2 is process ranges. That generates this file ranges.txt. So this is all the ranges that are 8 bytes or larger that appear to be free. And we can see we got some big chonkers here. I would expect the biggest one even to be the buffer between the stack and where other memory is being used. So I would have expected this one maybe to be the largest, but that's not the case. Somehow this looks to be the stack buffer, which, I don't know, it seems small to me, but like the stack that was used was small. But I only ran the game in this, when I did this first capture, I only ran it for like a minute or so. So maybe it didn't do much deep recursion, but there doesn't seem to be a lot of space left for the stack. But here we see like a huge, like this is way open. So I have high hopes for this region here. But anyways, so we now have our ranges generated. Now we can get this thing to generate a script. So we do command equal to 1, which is step 3. And I didn't even make it output a file. It just outputs the std out. But here you can see all my watch points that correspond to these ranges here. So now I'll just copy these. I got this file here, memscavscript.txt. So here's all my ranges in here. We run the emulator. We're gonna play it until we hit the title screen. Then we pause emulation. We go in here. We execute our scav script. We then have to start emulation again. That will make the watch points appear. And then we can start playing the game. And you'll see, even after one run, after eliminating just 1 minute's worth of memory accesses, the game already runs smooth. So that's beautiful. And let's do some things that I didn't do in my previous playthrough, in the first run through, which is like talk to this guy. And we'll also, you know, talk to you. And then we'll exit. And now we look at error.log, and it's not nothing, but it's a hell of a lot smaller. It's only 100 kilobytes. So this is now additional addresses that weren't accessed through my initial trace. So now I take this error.log, I put it into my RAM scavenger folder here. First thing, I run update map. That generates candidates 2. Now, because I'm a lazy program, I didn't automate this, I have to change this to candidates 2. I run the second command, which is process ranges, and I'm gonna get a new ranges file. And we can see that that big region wasn't touched, but I don't know, it's probably different. You can pause the video, you can go back and compare them, but I believe that these are different ranges. And then I run the third command, which is command 1, and I get my new list. I go into here, and if I paste, it should look a little different. Yeah, the values did definitely change here. So there you go. And as I play through the game, I'm gonna be shrinking the amount of free memory every time I access new paths in the code. And so the log file will be smaller and smaller, so I can play the game through for like an hour at a time and not blow up my disk with a giant log file. But yeah, I'm eyeballing this region right here, and I'm saying, that's a juicy territory. I'd love to, even if I could get like 2 kilobytes, you know, just a wafer thin slice of RAM, that's plenty for me. Because I also have another trick up my sleeve. But I'll leave that for the next video. Until then, thanks for watching. Hope you enjoyed this one. If you did, please click the like button, helps a lot. And I will see you again with some more ROM hacking warriors of the Eternal Sun.